Greetings humans, I've made this video so that we can be reminded how to find the LCM with three numbers or three monomials, and to explore a little further some fractions and negative exponents. So let's look at the LCM first. Let's say we're trying to find the LCM between 6, 8, and 20. Well, you can only really look at the LCM between two numbers at one time. So let's take a look at the LCM between 6 and 8. And the process is exactly as we explored before. You write the prime factorization for each, and the LCM between 6 and 8 is going to be what they have in common. Write it. With also being multiplied by the other factors as well. So the LCM between 6 and 8 can be found here, where 2 times 2 times 2 is 8, times 3 is 24. Okay, great. Now we've got to find the LCM between two of these other numbers. So if we looked between 8 and 20, let's see if we can find that LCM. Let's take 8. We already have the prime factorization from above. And 20's prime factorization, if you do a factor tree, should be like that. So the LCM, let's go ahead and see what they have in common, and write it. See what they have in common, and write it, and then represent the rest of them as well in this 5. So the LCM here is 2 times 2 times 2 is 8 times 5, 40. Now, if you can't readily find the LCM between these two numbers, you're going to have to find it over here. So let's do that. List the prime factorization for each first. And 40's prime factorization is 2 times 2 times 2, that's 8 times 5 is 40. And here we are, we're on our way. Write it, write it, write it, and list the other factors. And here's your LCM. We've got 2 times 2 times 2, which is 8, times 3 times the 5. We've got 24 times the 5, and so your LCM is 120. Just to review the process here, to find the LCM between 6, 8, and 20, we know that we can find the LCM between two numbers. So we took a look at 6 and 8 first, found its LCM for the 24, and then we took a look at 8 and 20 separately, found its LCM, this 40, and then we need to find the LCM between 24 and 40, and we found it to be 120. So this 120 is the LCM for those three numbers. Hooray! Let's go ahead and try this one. Maybe pause the video and try this one yourself. To find the LCM between three ideas, like we have listed here, it's best to look at two at a time. So let's take 15's prime factorization, 3 times 5, and let's take 30's, which is 3 times 2 times 5. Okay, we circle what they have in common, and we write it, and we circle what they have in common, and we write it, and we list any other factors we find. So of course, I hope you saw it already, but the least common multiple between 15 and 30 is that 30. Okay, well, we still got to look here between 30 and 50. Find the least common multiple between the two by writing each is prime factorization, 2 times 3 times 5 for 30, and then 50 is comprised of 2 times 5 times 5. To find the LCM, let's list as a product what they have in common. Here's the 2. They also share a 5. And now we've got to represent the other factors. There's a 3, and there's a 5. What do we have here? we've got 6 here, and we've got 25. 6 times 25 is 150. Okay, now we've got to find the LCM between 30 and 150. Hopefully you can already see that it's that 150, because 30 can go into 150. But if you couldn't see that, you can take each off to the side here and represent the prime factorization. Again, we know 30s and 150. I might have to do that over here. 2 times 75. Okay, and then maybe there's 3/4, right? And 75 cents. So 5 and 5. 2 times 3 times 5 times 5. And here we have it. And there's your LCM. And believe you me, that is 150. Hopefully this is making sense. Okie dokie, go ahead and try to find the LCM between these two numbers, and then try to find the LCM between these 3 numbers. Pause the video here and explore it on your own. I'm going to provide the answers in about 3 seconds, so pause it. Pause it. Pause it. Have you paused it? Okay, here are the answers. 72 d to the third, e to the second should be the answer for the first. And then the answer to the second, I'm doing it in my head right now. I think it's 60 x squared y squared. And again, don't shy away from this, because all you need to do is find the least common multiple between these two, and then find the least common multiple between these two, and I wish I had purple, and then separately, after you find those two, you'll find the least common multiple between the two that you found. And then that would be your LCM, which should be 60x squared y squared. Recall that if you take a to the second and multiply it by a to the third, that's just the same as saying a times a times a times a times a. So that means you have a to the fifth. Okay, great. That means that you have, in effect, added these exponents, when you are multiplying like bases. When you multiply like bases, you simply add the exponents and you'll find your answer. In this case, it's a to the fifth. Now, if we have like q to the 10th times q to the negative 8th times q to the negative 6th, that doesn't faze us because we're still going to add the exponents because we see multiplication of a common base. They're all q's. And so we have q to the 10th plus negative 8, all of this in the exponent land, and negative 6. When you combine all of those numbers, it looks like the answer should be q to the negative 4th power. Now, we're not simplified all the way here. We can make this a little more simple. If you remember, the property that says anything raised to a negative exponent is just the same as 1 over the positive version of that exponent. So we're not done with this answer. This answer should look of the form 1 over q to the 4th. Hooray! Good thing ain't nothing changing if you add some numbers up in there. If you've got 4x to the 9th, y to the 7th, multiplying, I don't know, 3x to the negative 7th, y to the negative 9th. The result is just, well, I'm going to use the commutative property to make this easier on myself. This is really saying all of this mess right here. Okay, now I'm going to multiply the numbers with the numbers and variables with variables. If variables have like bases and they're being multiplied, you can simply add these exponents. 9 and negative 7 will result in a 2. And then y is going to be to the negative second power. But wait a second. Through our studies in mathematics, we remember this idea. So we have 12x squared. But this idea with the negative exponent can just be put on the opposite side of the fraction bar. Right now, this number looks like this. It's over 1. But if we stick this idea down in the bottom, we can call it y squared down there. So let's see if we can do that. Okay, for some reason I can't erase that, so I'm just going to scribble it out. And we'll end up with y squared down here at the bottom. You feel me? So, the moral of the story is if you have negative exponents somewhere, you can bring them to the opposite side of the fraction bar and make them positive if you so desire. And that's truly the simplest form of the fraction. So in this case, to simplify this fraction, you can just say, well, it's really b to the 4th, that's all we have up top, and we have y to the 3rd on the bottom. But since this variable has a negative exponent, let's put it on the other side. And this one has a negative exponent, so let's put it on the other side. So you've got y to the 6th is going to end up in the bottom, and then x to the 4th will end up in the top. You're still not done, because there's more simplifying you can do. When all is said and done, it looks like you have y to the 9th on the bottom. Hooray! Here's another example. You have 9 over 3. Oh, wait. You have 9c to the 9th, d to the 3rd, and you have 3c to the 4th, d. Alright, if we needed to simplify this fraction, there's a couple of ways you can go about it. You can say, well, you've got 9 divided by 3, and then you've got c. If you remember dividing like bases, you can say c to the 9th minus 4, and then d to the 3rd minus the 1d that's on the bottom. And so your result is simply 3c to the 5th, and 3 minus 1 today is 2. So that's your result. Or you can think, going back to the beginning here, looking at this picture, you can just simplify the top with the bottom. You can realize that there's more c's on top because you have 9 of them, and you have 4 on the bottom, the difference of which is 5. And since there's more in the top, at the end you'll have 5 c's in the top. Looking at variable d, you've got 3 in the top and 1 in the bottom. The difference is 2. There's more on the top, so of course you'll be left with 2 on the top. 9 divided by 3 is a whole number 3. So there it is here. That just makes sense. I just want to throw this problem in there for kicks. Here we go. If ever you're multiplying two numbers that are written in scientific notation, again, multiply the number with the number. You've got 28. And multiply, well, I guess this is a number, but you can treat it like a variable because they're like bases, and you can add these exponents. If they're like bases, let's keep that base the same. That's 10, and then raised to the 3 plus 5 is 8. Now, if we wanted to represent this number in scientific notation, there's a problem, because this number has to be between 1 and 10. We can make it between 1 and 10 by moving its decimal over to the left. But if we do that, we need to compensate by moving this number to the right. So we'd make that 9 instead. So the scientific notation of the product of the two numbers above would be 2.8 times 10 to the 9th power. Yay! Good luck, humans, with your exploration of mathematics. If you have any questions with this right here, let me know, and I will be this to answer. Yay!